Most of us picture artificial intelligence as a single, omnipotent brain. You type a prompt into the void, the system hums, and a perfectly formed answer drops out of the black box. But when you take that single model approach out of a casual chat interface and drop it into a rigorous business environment, its reliance on internal memory becomes a massive liability. The breakdown usually happens in one of two ways. First, there is information failure. When a model lacks specific facts, it tends to guess, inventing plausible-sounding answers without evidence. Second, there is execution failure. If you feed one model too many complex competing instructions at once, it loses the thread and botches the workflow entirely. Because of this, enterprise developers are actively abandoning the idea that one giant model should do everything. Instead, they are wiring together modular, interconnected pipelines. Building an AI system that you can actually trust requires a strict separation of concerns. You have to decouple what the system knows from how the system acts. To solve information failure, engineers use an architecture called Retrieval Augmented Generation, or RAG. Rather than letting the AI rely on its own training data, RAG forces the model to use a custom, factual search engine before it generates a single word. This starts by breaking large documents down through chunking, slicing text into digestible segments. Next, segments are converted into embeddings, numeric representations of semantic meaning. Finally, these coordinates are indexed inside a vector database, creating an organized 3D grid to instantly locate related concepts. The user's query flows into the vector database, retrieving specific chunks of matching data. In steps 4 and 5, those facts are injected into the language model. A strict grounding rule forces the AI to generate a response derived exclusively from that provided evidence. Here we see the core rule in action: answer only what can be supported by the retrieved sources. By forcing the system to cite its source data, the model shifts from being a creative guesser to a highly verifiable answer engine. Once the AI has access to accurate facts, it still needs a way to execute multi-step workflows without getting tangled in its own logic. To solve execution failure, engineers use multi-agent orchestration. Instead of asking one massive model to handle a complex task, the work is divided among a team of smaller, highly specialized models. Looking at this workflow graphic, we see this sequential pattern. One agent completes a highly specific task, and its output serves as the direct, strict input for the next agent down the line. It ensures the work flows predictably in a single direction. In other scenarios, you might use a parallel pattern. Here, multiple specialized agents analyze the exact same data simultaneously through entirely different lenses, and their findings are consolidated into one final response. Relying on these simple, composable agent patterns forces predictable, linear logic. It breaks chaotic reasoning down into distinct, controllable steps that execute exactly as designed. To see how knowledge and action combine, look at how modern companies handle inbound customer service calls using multi-agent voice assistants. When a customer calls in, they hit a router pattern. A single greeter agent evaluates the user's initial intent. Its only job is to figure out what the caller needs and then dispatch them to the correct specialist. If the caller asks about an upcoming software launch, the greeter hands the call off to a technical readiness agent. If they have a PR question, they are routed to a marketing agent. Each sub-agent is restricted to its own isolated knowledge base. The marketing agent only searches marketing documents, and the technical agent only searches engineering files. Neither can see or access the other's domain data. This strict separation completely neutralizes cross-domain confusion. By keeping the knowledge and the action modular, the pipeline actively protects itself from the hallucinations and logic failures that plague monolithic models. Today, development has fundamentally shifted toward orchestrating coordinated teams of tiny, highly specialized models, all working together in perfect unison. This composable architecture gives engineers deep traceability. When a pipeline produces an answer, humans can audit the exact database chunk that was retrieved and pinpoint the specific agent that handled the request. As seen in this assistant interface, modular systems create much safer failure modes. By design, the pipeline is instructed to confidently admit uncertainty or flag conflicting information for human review rather than stubbornly inventing an answer. For a production environment, enterprise-grade trust requires a system of rigorous, composable architecture built from the ground up.